Okay. I would like to conclude the discussion concerning the use of the second quantization for the description of the electron-electron interaction term that we have already evaluated using the Hartree-Fock method and this later determinant. So in this case, what I would like to do is to do the same calculation that is similar to the one that was performed for the one-body operator. So to evaluate the yeah, the oops, to evaluate the expectation value of the electron-electron interaction potential using the second quantization formalism. And in this case, what we may do is just to, let's say, write something that resembles the expectation value of one two-body operator over two wave functions. But in this case, we replace the wave functions with two field operators, one corresponding to coordinate r and the other one corresponding to coordinate r prime. So we have one operator for coordinate r, another operator for coordinate r prime. Then we have the interaction potential and then the two wave functions, let's say the two field operators, again corresponding to r and r prime. For the moment, I will leave here just an expression for the potential. I will not write the actual expression for that. In principle, when we started the Hartree-Fock calculation, V of r minus r prime was the pure Coulombian potential, but then we saw that thanks to the screening effect of the electrons, the actual potential between the electrons is not the pure Coulombian one, but is the Yukawa one. So in this case, the correct expression would be the Yukawa potential for the electron-electron interaction. But just for the moment, I leave a general V, as I will make the substitution just at the end of the calculation. I just recall here the definition of the field operators. So in the case of the distraction operator, the expression of the distraction of both the distraction and the construction operators are based on the let's say distraction is better. Yeah, right. Okay. Are based on the distraction and construction operators defined on the level basis. So here I need the expression of the, let's say, wave function corresponding to level k and evaluated at the position that is equal to r. In this case, to make the calculation, I will use the same approximation that was used for the let's say that I used when we made the calculation to evaluate the exchange contribution after the Hartree-Fock calculation. So in that case, I just use the plane waves as wave functions to be used for the evaluation. So also in this case, I will use plane waves. So here, in place of the, let's say, phi k, I write e to the I k r c k, and then the we have also the square root of the volume as a normalization factor, and the same structure appears in the creation operator. So in this case, we have a summation over k of the conjugate of that. So I, with the minus sign in front, kr divided by the square root of the volume times c cross k. So these are the two expressions of a general distraction and creation field operator defined on the basis coordinates. And what I would like to do now is to substitute the expression of those operators into this expression here. Now I will need, here I have 1, 2, 3, 4 operators. So I need 4 summations here. At this point, I will use JK, MN as indexes of summation. I will skip index I because otherwise there is the risk to confuse that with the imaginary unit. So here I may write a summation over J, K, M, and N that are the 4 indexes that correspond to the summation of the 4 field operators. Then I have 1 divided by the square of the volume, because I have 4 times 1 divided by the square root of the volume. So I have, let's say, the product of 4 square root of v at the denominator. So at the end, I have just this v square here. Then there is the integral over d3r, the integral over d3 r prime, and then I have the conjugate of the first index. So I have I, j times r. Then I have the conjugate of the second, so minus k r prime, the V, the interaction potential of r minus r prime. Then I have these phi's that correspond to plus I m r prime. Then I have e to the I n r. Okay, since we have all phases here, it would be useful to express also the interaction potential in terms of a phase, or in terms of a combination of phases. So in this case, we may express V of r minus r prime using the Fourier, using the Fourier expression for that. So we have V of Q, the Fourier component of the potential corresponding to wave vector Q, e to the I Q, in this case, r minus r prime. Since we are evaluating, we have that as the argument of the function. So at this point, we need to have 5 summations over the wave vector. So we have the sum over j, k, m, n, and q, 1 divided by the square of the volume, the 2 integrals d3r, d3r prime, e to the minus I, j, r, e to minus, sorry, I forgot the imaginary unit here, I, k, r prime. Then we have v of q, e to the I, q, r minus r prime, then e to the I, m, r prime, e to the I, n, r. At this point, we have a total number of 6 phases, because we have 2 here, and if we split into 2 parts this exponential here, we have an additional number of 2 phases. We may group the phases with the coordinate r from the, and group on another side the phases corresponding to coordinate r prime. So in this case, if we just group here before including everything in the integral, we have e to the minus I, j, r. Then we have e to the qr. So I'm just grouping those corresponding to coordinate r. So we have this phase here, and this phase here. So e to the I and r. So those are those corresponding to coordinate r. Corresponding to r prime, we have e to the minus I, k, r prime. Then we have e to the minus r, q, r prime. And then we have e to the I, m, r prime. So those are the phases corresponding to the variable r prime. V of q is just a coefficient if we consider the integral over d3r and the integral over d3r prime. So when we make those integrals, we may just concentrate on the phases, and each integral corresponds to, so the integral over, just to make an example, minus ij r e to the e q r e to the I n r d3r corresponds to a volume times a delta where we have n plus q and j. So the request here is that this integral is different from 0 only if the summation of index wave vector n plus wave vector q minus wave vector j is equal to 0. So we may replace this integral with the volume times this Kronecker delta where we have those three indexes. So, and the same, due to the same method, the integral over d3r prime corresponds to, again, a volume. And then we have the Kronecker delta where we have m minus k q. And since the summation of m minus k minus q has to be equal to 0. So due to that, we may just rewrite this integral as 1 divided by 2. Then we have the volume that we have here and the volume that we have here allows us to simplify the square volume that we have here at the denominator. So let's say the volume disappears and we have just 1/2 the summation over j, k, m, and q of v of q times Kronecker delta n plus q j Kronecker delta m minus k q. And I'm sorry for that. This was the integral to the final operator, and I forgot to include here the construction and distraction operators. So I just include now the operators that I missed before. We have Cj that corresponds to the first phase. Then we have C cross K. Then we have Cm and Cn. So these four operators have to be included here and also in the next expression. So here I need C cross J, C cross K, then Cm and Cn. Okay, let's see if everything is fine. Okay, just to see what is the effect of the two deltas, I just rewrite everything on the next page. The expectation value is 1/2 summation over q, j, k, m, and v of q. Then I have the delta of q plus n j, another delta of m minus k q, and then c cross j, c cross k, c m, and c n. Yeah, so in this case, what we may try to do is to, let's say, use those two deltas to remove some of the indexes of summation. Now, if we use the second Kronecker delta, we have that q is equal to m minus k. So as a first step, we may remove the summation over q using this delta. the second delta at this point can be written as, so delta of q plus n j is equal of delta to, sorry, is equal to delta of m minus k plus n j. So I just rewrite that, since I may have a comment, I have a comment about that. So at this point, I remove the summation over q, I replace q with m minus k, and I have just one delta now, that is m minus k plus n, oops, j, and then the four operators. If you consider this, the constraint that is related to this delta, this requires that m minus k plus n is equal to j. If we take minus k on the other side, we have that this is equal to m plus n equal to j plus k. If you remember, j and k are the two indexes of summation that correspond to the distraction operators, and m plus n are the indexes of summation that correspond to the, sorry, the first two correspond to the creation operators, the first two correspond to the distraction operators. So in general, in this case, if you look at the structure of these four operators, we have that you destroy electron with wave vector n, you destroy electron with wave vector m. So this means that those two electrons has to be in the system. And then you create another electron with wave vector k and another electron with wave vector j. So this means that level n and level m correspond to the two electrons that are interacting. After the interaction, those two electrons will occupy level j and level k. So at this point, in the language of the distraction and construction operators, this is the equivalent of destroy those two levels because they're interacting. After the interaction, they will appear in new levels, so you have to create those electrons in the new levels. So at that point, you may suppose that electron n, electron corresponding to level n, and the electron corresponding to level m are the electron that feel the interaction. After the interaction, so you have this process that involves two electrons, and after the interaction, those two electrons disappear, and you have new electrons appearing in level j and level k. So level j and level k represents the final states after the interaction between level n, sorry, electron m and electron n. So here you have a requirement concerning the wave vectors of the, let's say, electron before the interaction. So this is before. And here you have the wave vectors after the interaction. And if you notice, since we are using plane waves, the wave vector is proportional, is equal, let's say, apart from a coefficient, the reduced Planck constant, the wave vector is equal to the momentum. So this is saying that the momentum, the overall momentum of the initial two levels has to be equal to the overall, to the total momentum after the interaction. So this equation tells you that momentum is conserved during the interaction, and that is fine, since if we use plane waves to describe the electrons, we are considering, let's say, free electrons. Free electrons means that the ground potential is uniform. So it's just like as if the interaction was in empty space. So the problem has full translational invariance. So at this point, we recover this momentum conservation during the interaction. Okay, now if we go back to this expression, we may try to make some modifications. So if we define m minus k as E, and we keep I as an index of summation in place of k. So the summation is over I, j, m, and n. So we have v of I, then we have this delta that is m minus k is I plus n j. Then we have c cross j. K in this case, referring to this equation, is m minus k, sorry, c cross m minus a. Then we have cm cn. Then we have to consider this additional Kronecker delta. So j in this case has to be equal to I plus n. So at this point, I suppress the summation over j. So suppressing that, we have 1/2 summation over I m n v of I. Then we have c cross I plus n c cross m minus I c of m c of n. Just for symmetry, let me just write E plus n as n plus c. I just switch the order of summation. So I have n plus e. So if you notice if you notice the structure of these four operators, you have the destruction of level n and level m, and the creation of two levels, m minus I and n plus I. So if you notice, they have an exchange. You have a change of wave vector. Here you have a decrease. Here you have an increase. But if you make the sum, you have again n plus m as you have at the beginning. And please notice that the variation of the wave vector that you have in the final electrons with respect to the initial electrons is equal to the wave vector corresponding to the Fourier transform of the potential. So this means that let's say, the contribution of the term where you have a change equal to I of the wave vector of the initial of both electrons, m and n, corresponds to the Fourier transform of the potential evaluated exactly at the variation I, in this case, of the initial and final, between the final and the initial wave vector. So if you want to represent this process, you may say that you have electron m and electron n. They have an interaction, and after the interaction, you have m minus I and n plus I. At this point, what is the additional requirement that we may include in this equation, in this final expression for the expectation value of the operator? This is an operator that has to be applied to the to a state of the system, and this state is the let's say, since we are using free electron, is the Fermi sphere. So if we want to evaluate the effect of that interaction, we have to apply this operator to the Fermi sphere. If you notice here, the Fermi sphere has to have these two initial levels, and then the state of the system will have will have no more level n and level m, but will have two more levels, m minus I, n plus I. So in this case, you have that as you apply this operator to the Fermi sphere, then you destroy a couple of levels and you create new levels. In principle, this operation may have at least two different effects on the Fermi sphere. One effect is that this, let's say, continuous process of destruction of levels and creation of levels may keep the Fermi sphere unchanged. So if you properly choose the values of m, n, m minus I, n plus I, then the Fermi sphere is stable under this sort of interaction. Another situation is that the all the levels m and n, groups of levels, sorry, couples of levels are progressively destroyed. Then you create new levels, but those levels are far out of the Fermi sphere. So at some point, the Fermi sphere may be destroyed because you continuously remove the levels within the sphere and you create new levels out of the sphere. So at this point, after some interactions, the Fermi sphere disappears because you destroy all the levels in the sphere and you create new levels outside. If we require that the system is stable under this kind of interaction, this means that if we start with a Fermi sphere at some point, then we expect to find again this Fermi sphere after some time. Then this means that the initial and the final level has to have a connection with the two initial levels has to have a connection with the final levels. Because if you destroy level m and level n and you create two new levels, those two new levels has to be equal to the initial ones. So the request is, if the request is the Fermi sphere has to be stable due to that kind of interaction, then we have two possible situations. Situation one, you have electron m and electron n, the interaction level m minus I and level n plus I. Level m minus I has to be equal to m, level n plus I has to be equal to n. So you destroy two levels, you create new levels, but the levels you create are exactly the levels you have destroyed. So in this case, we have that I is equal to 0 because m has to be equal to m minus I and n has to be equal to n plus I. This situation where let's say, each initial level is exactly equal to one of the final levels is called direct process, as each of the initial levels is exactly equal to the corresponding final level. Then we have another situation 2. In this case, we have level m, level n, the interaction. Then we have m minus I, n plus I. Level m minus I replaces level n, and level n plus I replaces level m. So in this case, you have an exchange because the initial level m ends up in the initial level n, and the initial level n ends up in initial level m. So we have what is called the exchange process. So the direct one, initial level is exactly equal to the final level. Exchange case, the two initial levels are exchanged after the interaction. So the electron that was in level m at the end is in level n, and the electron that was in level n at the end is in level m. If you remember, when we discussed the Hartree-Fock exchange term, we had also discussion concerning the spin of the electrons. In the case of the direct process, level M and level M after the interaction is again equal to level M. So at this point, irrespectively of the spin state of electron M, this is exactly equal to the final state. So for sure, irrespective of the level M, the spin state of the final state corresponding to level M will be exactly equal to level M. So no constraint concerning the spin state of level M or concerning level N. But if you look at the exchange process, the electron that is initially in level M, then at the end of the process jumps into level N. So due to the fact that the interaction does not involve here, there are no terms concerning the spin state. So the interaction in this case is not expected to, let's say, produce a spin flip or to make any modification to the spin state. So in this case, we have to require that the spin state of electron M and the spin state the spin state corresponding to level M and the spin state corresponding to level N have to be equal, because this electron at the end, so this electron here at the end jumps in level N. So again, since we have no modification of the spin of the electron during the process, what we need to have is that the two spin states are equal. So this situation resembles the situation that we have obtained when we consider the Hartree-Fock calculation of the electron-electron interaction. And what I would like to do now is to start from this expression and to see what happens from using that expression, trying to include in the expression of the operator the number of particles operator. So I will first try to describe what happens when I is equal to 0, and then I will, I forgot to include the constraint here concerning the index. So in this case, we have that m minus I has to be equal to n. So I is equal to m minus n. And the same condition comes from the constraint that n plus I has to be equal to n. So we just have to remember two situations here. Direct process I equal to 0, exchange process I is equal to m minus n. So at this point, the calculation may be concluded if we just fix the two values of the indexes. So yeah, let's start with I equal to the I equal to 0 case. So in this situation, we have 1/2, no summation over I, but just over m, and then we have v0, so the Fourier transform corresponding to wave vector equal to 0. So we have C cross n, C cross m, Cm, Cn. Please note that here we have the value of the Fourier transform of the potential corresponding to index equal to 0. If if V was the pure Coulombian potential, then V0 is infinite, because the Fourier transform is 1 divided by q squared. So in this case, V0 is infinite. But if we don't use the pure Coulombian expression, but we use the Yukawa term, then at this point, V of 0 is just a number. So no problems with the calculation in this case. To change the structure of the operators here, we have to take n and, let's say, exchange them. We have to make two exchanges. So to take Cn close to C cross n. So at that point, we have the number of particles operator corresponding to level n, sorry, and we also have here the number of particle operator corresponding to level m. So the first thing we need to do is to exchange this Cn with Cm. What we have is that if we consider the anticommutator is 0, so we have that Cn is equal to minus Cm. So we may replace Cn with Cm just by adding a minus sign in front of the summation. So we have minus 1/2 sum over m and n of V0 C cross n C cross m Cn Cm. At this point, we need to exchange C cross m and Cn. In this case, the commutator is that C cross m Cn is equal to delta mn times identity. So we have that this is equal to minus 1/2 summation over m and n of V0 C cross n. Then we have the same terms here exchanged just with a minus sign in front. So we have minus Cn Cm C cross m, and this is just the anticommutator. Then we have plus delta mn times identity, and then the last term is Cm. So we have minus 1/2, at this point, just plus, minus here, we have a plus sign, 1/2 sum over m and n of V0 C cross n Cn C cross m Cm. So this is the first term. Then we have minus 1/2 sum over m and n of V0 C cross n. Then we have Cm and delta mn. So if we apply this delta, this transforms into 1/2 sum over m and 0. Here we have number of particles operator corresponding to level n and number of particle operator corresponding to level m. Then minus 1/2 sum over m of V0 C cross n Cn. Okay, and before going on with a further modification of this term here, I just see what happens when we consider the exchange process, that is I equal to m minus n. So this is the exchange, and the previous one was the direct. So in this case, we have 1/2, the summation over I disappears, so we have just m and n. Then we have v of m minus n. Then what we have is that, here we have C cross m, C cross n, and then we have Cm, Cn. If you notice here, to build up a structure where we have this construction and destruction operator corresponding to the same level, we just need to exchange these two operators here. So when we consider these two operators, we may just use the second commutation rule. So we may replace this with minus 1/2 summation over m and n of v of m minus n. We have c cross m, cm, c cross n, cn. So I've just exchanged those two terms. Then, and with the minus sign in front, and then I have plus 1/2 summation over m and then of v m minus n. At this point, I have c cross m. Then in place of the central terms here, I have just delta m n times identity, and then I have the last operator, cn. And this is equal to minus 1/2 summation over m and n of v m minus n, number of particle operator corresponding to level m, number of particle operator corresponding to level n. Then I have plus 1/2. Due to this Kronecker delta, m has to be equal to n. So you have just a summation over. Sorry, before I wrote m as an index of summation, but in this summation I left index n. So please just include here also index m for the operators, because the index of summation is m. So here we have v of 0 because m has to be equal to n. Then we have c cross m, cm. If you notice, here we have this result. For the exchange term, we have another result. But at the end, the results coming in the two situations have to be summed together to find the final expression for the energy. So when you sum those terms, you have that this term here and this term here are exactly equal. The only thing that changes is the sign in front, because you have a minus sign here and a plus sign here. So when you sum up these two contributions, you have that this term can be simplified with that term. So at the end, we are left with just this contribution for what concerns the direct term, and this contribution for what concerns the exchange term. So what I'd like to do is just to rewrite this term here and this term here, just to see whether it's possible to find an expression for those terms that is similar to the expression that we found for the Hartree-Fock situation. And yeah, this is not a long calculation, so if for you it's fine, I just finish the calculation, and after the calculation I make the break. So let's start with the direct term. So the direct term is 1/2 summation over m and n of V0, number of particle operator corresponding to level. I don't remember, was that m or n? Okay, thank you. And then number of particle operator corresponding to level m. Yeah, in this case, we may replace the here the expression for V0 with the actual expression of that term, because V0 is the Fourier component corresponding to wave vector equal to 0. So we have and here we have no phase due to the fact that, again, we are just evaluating the term corresponding to Q or K equal to 0. So here we have 1/2 the summation over m, and then we have the integral over d3r of v of r, number of particle operator corresponding to n, number of particle operator corresponding to level m. And yeah. In this case, sorry, I forgot the volume. In this case, now we may do something like this. We have the d3r integral divided by the volume. Then we have O of r, the number of particle operators. Then I may include here another integral over d3 r prime. In this case, there is no variable of integration involving r prime. So the integral over d3 r prime just gives me a volume. To compensate that, I divide by a volume. So in this case, I introduce this new term here. So I add the integral over d3r prime, and I divide by the volume to compensate the additional volume that comes from the integral. And then I make another modification. So integral d3r, d3 r prime. At this point, I make a translation. So I make a change of variables concerning the integral, just the integral over r, and I make a translation equal to minus r prime. That translation doesn't affect the volume element, just affects the expression of the potential. So this is the, let's say, again, we are using an operator. At this point, if we evaluate those two operators, so if we want to evaluate the value corresponding to nn or nm over the Fermi sphere, then that value is given by the Fermi-Dirac distribution corresponding to level n and the Fermi-Dirac distribution corresponding to level m. So at this point, if we're supposed to apply that operator to the Fermi sphere, what we have is 1/2 summation over m, and then d3 r prime v of r minus r prime, and then we have the Fermi-Dirac distribution, the Fermi-Dirac distribution value corresponding to energy n, and the Fermi-Dirac distribution value corresponding to energy m. So corresponding to I just write that as f of n to say the Fermi-Dirac distribution corresponding to level n, and f of m, that is the Fermi-Dirac value, the distribution of the the value of the Fermi-Dirac distribution corresponding to level m. If I just let's say, write the full expression of V, here, for simplicity, I just use the Colombian one, but let's so just not to stress what is the actual value of V, I just write that V of R minus R prime is equal to E squared V tilde R minus R prime. I just take the electronic charge out of the expression of the interaction potential because I need that for the next transformation. So in this case, this is equal to 1/2 summation over M and then D3R prime E squared. And I'm sorry, I forgot to copy this volume squared here and also the volume squared that I had in the initial integral. So here I have a volume squared V tilde of R minus R prime Fn Fm. We have nearly finished. If we write E squared as minus E divided by V times f of k, then we have the interaction potential, and then we have minus E divided by volume times Fm. Sorry, this is N. What is this? And the same meaning can be applied to the other term here. Here, what we have is minus, if we consider the electrons to be represented by plane waves, the charge density corresponding to one electron is uniform over the volume. So minus C divided by volume is just the, let's say, charge density corresponding to level, in this case, N. And here we have the charge density uniform over the volume, M. So we may write this as the summation over M and then of D3R prime charge density corresponding to level N. I know that the charge density is uniform, but please let me write that as R, but we know that charge density is uniform, so no actual coordinate dependence. Sorry, I forgot to include the Fn, then we have V. So the Fermi-Dirac distribution is there just to, let's say, be sure that that electronic state is actually occupied. So if we want to, we may, let's say, since we consider the electrons to be described by the Fermi sphere, if T is equal to 0, we may also remove Fn and Fm and just write here that this summation is just over the indexes that are within the Fermi sphere. But to be more general, we may just leave there the Fermi-Dirac distribution and just leave the summation without any constraint. So in this case, we have something that resembles the, let's say, charge density corresponding to electron N interacting with the charge density corresponding to electron R prime. So this is something that resembles the direct process, the direct term in the Hartree-Fock approximation. And if you want to have an expression that is even more close to the initial one of the one corresponding to the direct term, we may just remember that the charge density in the Hartree-Fock approximation was written to be equal to minus E square modulus of the wave function corresponding to the level. So here we have minus C square modulus of the wave function corresponding to a level M. So since the square modulus is the conjugate times the non-conjugate value of the wave function, if we expand the square modulus and we group all the parts that are conjugated on one side and all the parts that are not conjugated on the other side, what we have is conjugated. So we have phi n conjugated r, phi m conjugated r prime. Then we have e squared v of r minus r prime, and then we have phi n of r phi m r prime. So if you expand this to here and you group the wave functions, then you have the same expression with two conjugated wave functions on this side and the corresponding two non-conjugated values on the other side. So this is actually what was within the integral in the direct term when we considered the application of the electron-electron interaction potential to this later determinant. So yeah, this is actually what we observed in that case. And if you don't mind, in the second case, I will do things more rapidly. So if we consider the just the exchange term, in the exchange term, we have minus 1/2 summation over m and n of v m minus n So if we do exactly the same, we apply exactly the same procedure. So when we apply those operators, so when the two operators are applied to the Fermi sphere, then we have the values of the Fermi-Dirac distribution corresponding to level n and level m. And then in place of v of m minus n, we may write 1 divided by the volume, the integral over d3r of v of r e to the so if we replace the let's say the Fourier transform of in this case v of m minus m, and at the end we follow exactly the same procedure that we have used before. And please note that now when you make the when you replace r with r minus r prime, as I did before, in this case you have 4 terms in the phase. So you have e to the minus r prime m minus n I. So you have a total number of 4 phases. So you have 4 phases, and you have e to the minus r m I, e to the, I know I keep the negative sign on one side. So the other negative sign, sorry, is minus r prime n I. And then I have the phases with the positive sign. The phases with a positive sign are e to the r prime mi, and then I have, so in this, yeah, r prime and e to the r n I. Yeah, so in this case, if I now write down the full integral, I have minus 1/2 summation over m and then of the integral of d3r prime. I have one volume coming from the definition of the Fourier transform and another volume coming from the introduction of the d3r prime integral. Then I have e to the minus I m r, e to the minus I n r prime. Then I have e squared, the interaction potential, and e to the I m r prime, e to the I n r. Now, if you write this v squared in this term, so if you use the square of the volume to introduce, to have the normalization factors for the phases, at this point you have minus 1/2 summation over m and n of d3r prime, and then this is the conjugated of level m in position r. This is the conjugated of level n in position r prime. Then I have e squared interaction term. Then I have phi of m in coordinate r prime and phi of n in position r. And please note here that on this side we have, for instance, that the electron in level m is evaluated, sorry, that the wave function corresponding to level m is evaluated in position r, and on the other side the same wave function is evaluated in position r prime. So it's not possible to rewrite this term as a square modulus. Sorry, we may not couple these two terms here to write the square modulus as we did in the direct term. So in this case, we have the exchange of the electrons from this side of the integral on the other side of the integral. And this is the same structure that we observed for the exchange term in the Hartree-Fock method. And please forgive me, I've forgotten the delta, the Kronecker delta related to the spin states. So here we have delta sigma m, sigma n, and also here delta sigma m, sigma n. So what we have at the end is exactly the same term that we found in the case of this later determinant, the application of the Hartree-Fock approach using this later determinant. And yeah, before concluding this part of the lesson, I would like just to recall that in all the calculation, we never had to consider the fact that the global wave function has to be antisymmetric. So we completely forget the symmetry constraints related to the electrons. We just focused on the calculation because the antisymmetry properties were ascribed to the operators. So in this case, we just wrote the expression of the expectation value and made the calculation completely forgiving any symmetry requirement or the fact that we have to fulfill the pole exclusion principle, because that was, all those details were included in the construction and destruction operators. Okay, I'm sorry, I'm a bit late. So do you have questions or comments concerning this calculation? Okay, so I stop the registration, we make a break, and then after the break, I go on with the second part.